Welcome back. In this lesson, we're going to be looking at the factors that can affect the performance of a CPU. By the end of the lesson, you should be able to understand what is meant by a core, a cache, and a clock in a CPU, and explain how they can affect the performance of a CPU. You should also be able to understand the purpose and use of an instruction set for a CPU. Now, the performance of a CPU refers to how quickly the CPU can process an instruction. And this is very important as the more instructions that can be processed in a second, the higher the performance of a CPU. Now, most people want a very high performing CPU, so they're not just waiting around and frustrated with their computer because it takes too long to perhaps open a document or load an application. So what are the factors that influence a CPU's performance? The first thing to consider is the role of the system clock itself. The clock defines the clock cycle, and this synchronizes all computer operations. And we know that from the von Neumann architecture. The control bus transmits timing signals, ensuring everything is fully synchronized. And by increasing the clock speed, the processing speed of the computer is also increased. Now, a typical current value is 3.5 gigahertz, which means 3.5 billion clock cycles a second. Of course, we've got processors at the moment that can go up to 6.2 gigahertz, but they're very expensive, so the typical CPU will be working at this particular level. Now, although the speed of the computer may be increased, it isn't possible to say that a computer's overall performance is increased as a result of using a higher clock speed, because other factors come into play as well. So let's start by looking at these. The first factor that you need to consider is the width of the address bus and the data bus, and that affects the computer's performance. So having a really fast CPU which operates at say 64 bits and having an address bus or a data bus which has a width of 32 bits could lead to a bottleneck. So increasing the bus width can have a direct improvement on a computer's performance. Another factor is overclocking. The clock speed can be changed by accessing the BIOS, which is the basic input-output system, and this is a bit of firmware, and you can change the settings inside there. However, when you use a clock speed that's higher than the computer was designed for, that can lead to problems. And the two main problems are that the execution of instructions outside design limits can lead to unsynchronized operations, like you complete an operation before the expected time, and that could lead to a crash. Overclocking can also lead to serious overheating of the CPU, and that could lead to unreliable performance as well. And sometimes you see people using liquid nitrogen and fancy techniques to cool overclocked CPUs. Now, saying that, some CPUs are also designed to boost their speed to a higher level temporarily to get performance, and then they drop back down to their native operating speed. So you might have a 3.5 gigahertz processor that can boost to 4.2 gigahertz for maybe a short amount of time and then come back down. However, the kind of overclocking we're talking about is going beyond the limits of the manufacturer, and that can lead to some issues. Of course, you get some performance gain, but then you also have these serious concerns. The next factor we are going to talk about is the use of cache memories, which can also help in improving the CPU's performance. Unlike RAM, cache memory is located near the CPU or inside the CPU itself, which means that it has much faster data access times than RAM. So if you think about hard drives and SSDs having slower speed than RAM, and data has to be transferred to RAM so the CPU can operate quickly, that same type of relationship is between RAM and cache. So cache stores the frequently used instructions and data, and that means that the CPU can access them faster. That means it can perform better. However, when a CPU wishes to read memory, it will first check out the cache and then move on to the main memory. Now, this can also cause a bit of a performance issue that sometimes you're taking an extra step to get to the data. So in certain cases, in certain scenarios, the speed or the performance can be slower. The final factor is the use of a different number of cores, which can also help computer performance. Now, one core is made of an ALU, a control unit, and registers, and many computers now are dual core or quad core or octa core. Dual core is 2 CPU cores, quad core is 4 CPU cores, and octa core is 8 cores. And even beyond that are possible. There are CPUs which have 12 or even 16 cores available to them. The idea of using more cores alleviates the need to continually increase clock speeds, because suddenly you can process instructions in parallel. That means you can do 2 instructions or 4 or 8 instructions at once. Doubling the number of cores doesn't necessarily double the computer's performance, because we still need to take into account the need for the CPU to communicate with each core, and this reduces overall performance. An example is that in a dual core, the CPU communicates with both cores using one channel, therefore some of that improved performance gain is reduced. And if you've got a quad core, that basically means you are now operating between 5 possible channels, and that can take a performance hit as well. So to summarize everything, a computer's performance can be changed by altering bus width, clock speed, the use of multi-core CPUs, and the use of cache memory. Increasing the bus width for both the data and address buses increases the performance and speed of a computer system. Increasing the clock speed will potentially increase the speed of a computer, but can lead to overheating or crashes. Use of cache memory can also speed up a CPU's performance, and so can the use of multiple cores. But both of these can also lead to some performance hits in certain scenarios. For example, cache requires an extra step to access data that might be in RAM. You are a bit slower in that case. And the use of multiple cores can lead to losing some of those gains because of synchronizing the communication between the various different channels that connect the cores. Okay, let's move on to the instruction set. Now, in a computer system, instructions are a set of operations which are decoded in a sequence. So an instruction set is basically a list of all the commands that can be processed by a CPU, and the commands are machine code or binary. Now, each operation will instruct the arithmetic logic unit and the control unit, which are part of the CPU, and it instructs them to do something. So an operation is made out of two parts, an opcode, operation code, and an operand. The opcode informs the CPU what the operation needs to do, for example, add, subtract, things like that. The operand is the data or the address which needs to be acted upon. So that normally refers to data in a register. For example, if you have an operation called LDA 100, that basically means load into the accumulator the value 100. The LDA is the opcode and the 100 is the operand. Now, since the computer needs to understand the operation to be carried out, there's a limited number of opcodes that can be used, and these are listed in the instruction set. So all software running on a computer will contain a set of instructions, and these need to be converted into binary. And all of these conversions, the binary values, are stored in that instruction set. So you could possibly think of it as an ASCII or Unicode table equivalent, but for commands. Now, one example of an instruction set is for the x86, a common CPU standard that's used across many modern computers. Although different computer manufacturers will adopt their own design, if a computer design is based on an x86 architecture, then all designs will share almost identical instruction sets. So certain Intel and AMD CPUs are almost identical in that respect because they can all run the x86 instruction sets, even though they are designed differently by different manufacturers. So x86 becomes a standard. Now, common instruction set operations include add, JMP for jump, LDA for loading something into the accumulator, commands like that, and all of these are part of the instruction set. A computer can't function without accessing an instruction set. So make sure you remember the definition for an instruction set and how it's used. Okay, that's all for today. Hopefully you should be able to answer the following questions. What are the factors that can help improve the performance of a CPU? What is the role of an instruction set? How can altering the bus width improve performance? Explain how a quad-core CPU might not lead to a 4 times performance improvement. And what are the disadvantages of overclocking? If you do have any questions, as usual, please do get back to me. Otherwise, I'll see you in the next one.